Introduction to Zero-Knowledge Proofs. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today, we're venturing into one of the most fascinating and powerful concepts in modern cryptography, the zero-knowledge proof, or ZKP. Imagine you could convince someone you know a secret, like a password or the solution to a puzzle, without revealing any information about the secret itself. That's the magical promise of a ZKP. It's a method where one party, the prover, can prove to another party, the verifier, that a given statement is true. The verifier learns nothing other than the fact that the statement is, indeed, true. The diagram on the slide illustrates this fundamental interaction. The prover possesses some secret knowledge, or a witness. They construct a special proof and send it to the verifier. The verifier checks the proof and becomes convinced of the prover's claim, but they gain zero knowledge about the secret witness itself. This idea has profound implications for privacy and security. In this presentation, we'll explore the properties that make ZKPs work, look at a simple protocol, and see how they are revolutionizing fields like blockchain and digital identity. The three core properties of ZKPs. For any protocol to be considered a valid zero-knowledge proof, it must satisfy three critical properties, which are the pillars of its integrity and security. First is completeness. This property guarantees that if the prover's statement is true and both parties follow the protocol honestly, the verifier will always be convinced. It is the assurance that the system works as intended for legitimate proofs. Second is soundness. This is the security guarantee against a cheating prover. If the prover's statement is false, they have only a negligibly small chance of tricking an honest verifier into accepting the proof as valid. In other words, you cannot fake a proof for a statement that is not true. The third, and most famous, property is zero knowledge. This property ensures privacy for the prover. If the prover's statement is true, the verifier learns absolutely nothing about the underlying secret information used to create the proof, other than the fact that the statement is true. The verifier cannot go back and reconstruct the secret from the proof. Together, these three properties create a powerful cryptographic tool that is both robust and privacy-preserving. Interactive versus non-interactive ZKPs. Zero-knowledge proofs can be broadly categorized into two types: interactive and non-interactive. Interactive ZKPs, the original form, require a live, back-and-forth conversation between the prover and the verifier. As the diagram illustrates, the prover makes a commitment, the verifier sends back a random challenge, and the prover sends a response based on that challenge. They might repeat this process multiple times to increase the verifier's confidence. This is like a live interrogation. While interactive proofs are often simpler to understand and design, they have practical limitations. They require both parties to be online at the same time and are not suitable for systems where proofs need to be publicly verifiable by anyone at any time, like a blockchain. Non-interactive ZKPs, or NIZKs, solve this problem. In a NIZK, the prover can generate a complete proof in a single step, without any communication from the verifier. This proof is a self-contained piece of data that can be published and checked by anyone. This is achieved through a clever cryptographic trick called the Fiat-Shamir heuristic, which we will discuss later, that uses a hash function to simulate the verifier's random challenge. Because of their flexibility, non-interactive proofs are what we typically use in real-world applications. Classic example: the Socialist Millionaires Problem. To build some intuition before we dive into the math, let's consider a classic problem that ZKPs can solve: the Socialist Millionaires Problem. Imagine two millionaires, Alice and Bob, who want to find out if they have the same amount of wealth without revealing the actual amount to each other. This is a perfect use case for a ZKP. They are the prover and verifier to each other. The statement they want to prove is our wealth is equal. The secret information, or witness, is the actual amount of their wealth. Using a ZKP protocol, They can engage in a series of exchanges that will result in a simple yes or no answer to the question, "Are we equally rich?" At the end of the protocol, they will both know the answer, but neither will have learned anything about the other's net worth if they are not equal. This problem highlights the power of ZKPs to enable secure computation on private data, a concept that is incredibly valuable for privacy-preserving systems. The mathematical foundation. The magic of zero-knowledge proofs isn't actually magic, it's clever mathematics. Most ZKP constructions are built upon what are called hard problems in computer science. These are problems that are easy to compute in one direction but are believed to be computationally infeasible to reverse. The most common foundation is the discrete logarithm problem, especially in the context of elliptic curve groups, which we've discussed before. As a quick recap, it's easy to perform scalar multiplication to compute a public key p equals x times g from a private key x. However, given only the public points p and g, it's practically impossible to find the secret scalar x. This one-way function is the perfect building block for a ZKP. The prover can use their knowledge of the secret x to construct a proof, and the verifier can check the proof using only the public point p. The difficulty of the discrete log problem is what guarantees that the verifier cannot reverse engineer the proof to discover x. This mathematical asymmetry is the engine that powers the security of these protocols. A simple ZKP protocol, Fiat-Shamir. Let's walk through a simplified, interactive ZKP that demonstrates how someone can prove they know a secret without revealing it. This is based on the Schnorr identification protocol, which is a classic example. Let's say Peggy, the prover, wants to prove to Victor, the verifier, that she knows the private key x corresponding to her public key p. The diagram on the slide outlines the three-step interaction. It begins with Peggy making a commitment. Then, Victor issues a random challenge. Finally, Peggy provides a response that depends on her secret, her commitment, and Victor's challenge. This three-step process of commit, challenge, respond is a fundamental pattern in many ZKP protocols. Through this interaction, Peggy can convince Victor that she must know X, because, as we'll see, crafting a correct response without knowing X is impossible. Commitment. The protocol begins with the commitment step. This is where Peggy, the prover, commits to some random information before the challenge is revealed. This is crucial to prevent her from cheating. She generates a secret random number, a nonce, which we'll call K. Just like in signature schemes, this nonce must be unpredictable and used only for this one proof. She then computes a public commitment point, R, by multiplying the public generator point G by her nonce K. So, R equals K times G. She sends this point R to Victor, the verifier. By sending R, Peggy is essentially placing a sealed envelope on the table. She has committed to the value K without revealing it. Victor knows R, but due to the discrete logarithm problem, he cannot figure out what K is. This commitment locks Peggy in, so she can't change her mind after seeing Victor's challenge. Step 2. Challenge. Now that Peggy has committed to her secret nonce by sending the point R, it's Victor's turn to act. Victor, the verifier, needs to issue a random challenge to Peggy. In this step, he simply generates a random number, which we'll call E. This number is the challenge. He sends this number E back to Peggy. The randomness of this challenge is critical for the security of the proof. If Peggy could predict the challenge E in advance, she might be able to craft a fake commitment R that would allow her to pass the verification check without actually knowing her secret private key X. By making the challenge random and unpredictable, Victor ensures that Peggy's only path to success is to honestly follow the protocol using her secret knowledge. Response. Peggy has now received the random challenge E from Victor. This is the final step where she must use her secret knowledge to construct a valid response. She calculates a new value, S, using the formula you see on the slide. S equals K plus E times X. Here, K is her secret nonce from the commitment step, E is Victor's challenge, and X is her secret private key that she is trying to prove she knows. This formula combines all the elements of the protocol: her secret commitment, the public challenge, and her secret witness. She then sends this calculated value S back to Victor. This single number, S, is her response. It contains the proof of her knowledge, but in a way that is scrambled with the random nonce K, preventing Victor from simply solving the equation for X. Verification. Victor now has all the pieces he needs to verify Peggy's proof. He has her public key P, her commitment R from step 1, the challenge E that he created in step 2, and her response S from step 3. To verify, he checks if a single equation holds true. S times G equal operator R plus E times P. He computes both sides of the equation independently. On the left side, he computes S times G. On the right side, he computes E times P and adds the result to the point R. If the point on the left is identical to the point on the right, he is convinced that Peggy must know the secret X. Why? Because the only way Peggy could have constructed an S that satisfies this equation for a random E is if she knew the value X that makes P equal operator X times G. We've already proven that this equation is algebraically sound. This check satisfies the completeness and soundness properties. And because S is randomized by K, the proof satisfies the zero-knowledge property, as Victor cannot isolate X from the equation. Making it non-interactive. Fiat-Shamir heuristic. The interactive protocol we just saw is great for understanding the mechanics, but it is impractical for many real-world systems. To make it non-interactive, we use a clever trick called the Fiat-Shamir heuristic. The key idea is to replace the verifier's random challenge with a non-random but unpredictable challenge that the prover generates themselves. This is done using a cryptographic hash function. Instead of waiting for Victor to send a challenge, Peggy can simulate it. After she computes her commitment R, she hashes R along with her public key P and the message M, if any, to produce the challenge E. That is, E equals H, open parenthesis, P or R or M, close parenthesis. Because the output of the hash function is unpredictable, she cannot craft R to get a favorable E. This allows her to compute her response S and bundle the proof as the pair R, S. Now, anyone can verify this proof. A verifier will simply recompute E using the same hash function and then perform the same verification check. This simple but brilliant trick transforms an interactive protocol into a non-interactive one that can be posted publicly and verified by anyone. Modern ZKPs. ZK-SNARKs and ZK-STARKs. The simple protocol we examined is just the tip of the iceberg. Modern ZKP research has led to incredibly powerful and complex systems, most notably ZK-SNARKs and ZK-STARKs. ZK-SNARK stands for Zero Knowledge Succinct Non-Interactive Argument of Knowledge. The key word here is succinct, which means the proofs are extremely small and very fast to verify, regardless of how complex the original computation was. This makes them ideal for blockchains. However, most SNARKs have a downside. They require a trusted setup, a special ceremony to generate initial public parameters. If this ceremony is compromised, the entire system's security can be broken. ZK-STARK stands for Zero Knowledge Scalable Transparent Argument of Knowledge. STARKs are a newer technology. Their main advantage is being transparent, which means they do not require a trusted setup. They rely on public randomness. They also have the advantage of being scalable, as the time it takes to create a proof grows very slowly with the complexity of the computation. While STARK proofs are larger than SNARK proofs, their transparency and quantum-resistant properties make them very attractive for many applications. Applications of zero-knowledge proofs. The potential applications for ZKPs are vast and transformative. In the world of blockchain and cryptocurrencies, they are a game-changer. Privacy coins like Zcash use ZK-SNARKs to shield transaction details, allowing for completely anonymous transactions. ZKPs are also being used for scalability in what are called ZK-Rollups, where thousands of transactions can be bundled into a single, tiny proof that is posted on the main blockchain, drastically reducing fees and increasing throughput. Another major area is digital identity, often called self-sovereign identity. With ZKPs, you could prove you are over 18 without revealing your date of birth, or prove you are a citizen of a country without revealing your name or passport number. You control what information is revealed. Finally, ZKPs enable verifiable computation. You can outsource a heavy computation to a powerful cloud server, and the server can return the result along with a ZKP that proves the computation was done correctly, without you having to rerun it yourself. This allows you to trust the results of computations performed on untrusted machines. Summary and conclusion. We have journeyed through the incredible world of zero-knowledge proofs. We learned that they allow a prover to convince a verifier that a statement is true without revealing the secret information behind it. We saw that their power comes from three core properties: completeness, soundness, and the crucial zero-knowledge guarantee. We walked through a classic interactive protocol and understood how the Fiat-Shamir heuristic transforms it into a more practical, non-interactive proof. We also touched upon the cutting edge of ZKP technology with SNARKs and STARKs, which are making these complex ideas practical for the real world. From private transactions on blockchains to a new paradigm of digital identity, ZKPs are not just a theoretical curiosity, but they are a fundamental building block for a more private and secure digital future. Their ability to separate the act of verification from the revelation of information is truly a revolutionary concept in computer science. Thank you for your attendance. Please consider subscribing to the channel.